Hello, hello. Yeah, okay. So I was told that in the last class, hysteresis graph is not was not done. So let me just quickly explain that. Hysteresis, R-E. I hope the spelling is correct. Okay, so let's see what that hysteresis graph is. You have a magnetic material and you apply some external field. Okay, let's say B naught. And you divide that by mu naught, you're gonna get H. Okay. So what I'm going to do is I will plot the magnetic field that is developed within the material versus the H that is put externally. So H versus B or B versus H it is. So when H is 0, which means externally there is magnetic field. So in that case, there won't be any magnetic field developed within the material. So B will also be 0. Slowly, if you increase H, B will also increase. Okay, so will increase like this. Okay, so as you increase H, the domains get more and more aligned, and so B also becomes larger. What happens is after a certain point of time, B doesn't increase much; it kind of saturates. This happens when all the domains are perfectly aligned. Okay, once all the domains are perfectly aligned, they cannot align anymore. So what you see is something like this. Okay, so there will be a saturation in the magnetic field. Okay, this is called saturation magnetic field. That is the maximum that you can produce inside the material. Now, from then on, if you decrease H, you expect to return to the origin along the same graph. But what happens is the graph goes like this. Okay, so if you decrease H and make it 0, turns out that there will still be some magnetic field inside the material. Okay, so that leftover magnetic field or that retained magnetic field is called retentivity. Okay, retentivity. It's the magnetic field when H is equal to 0. Okay, so now whatever magnetic field is retained, I would like to make it 0 completely. So what I'm going to do is I'm going to revert the direction of H. Okay, I'll make it H negative. I'll make H negative, which means H is now in this direction. Okay, so that will uh, make sure that whatever alignment of domains have happened inside the material, that alignment will go away. And then finally, for some value of H in the negative direction, all the retained magnetic field will become 0. Okay, so this is the value of H at which the retained magnetic field becomes 0. So that is called coercivity. Okay, now from here on, if you, yeah, any questions? Okay. So from here on, if you further decrease H and make it even more negative, B will also start becoming more and more negative. And again, at some value of H, it will saturate. Okay. So all the domains are now aligned in the other direction perfectly, and you cannot align them anymore. So that's where again you'll get a saturation magnetic field. So from here again, if you want to reduce the magnetic field, you decrease H, okay, and make H 0. So here is where H becomes 0, but still, again, the same thing happens. The material will retain some magnetic field. That is again called retentivity. So to remove that field that got retained, you just have to make H positive now. Okay, and at this positive value of H, whatever negative magnetic field that got retained becomes 0. Further, if you increase H, B also increases, and again it gets saturated. So that is a cycle, guys. Okay, so this is also again coercivity. Okay, so this is your hysteresis graph. Things to note: Retentivity, coercivity. This is saturation, magnetic field. This is also the same thing. And the area under the graph. Okay, which area? This area. That area will give you heat lost per unit volume in one cycle. Okay, we don't have to worry about the proof of that. It's not there in your syllabus, so don't worry about that. So if you don't want to produce a lot of heat, then better choose material whose area is very, very less. That's what we do in electromagnets and transformers. Electromagnets and transformers. So in these devices, we keep changing the direction of magnetic field inside the material by changing the direction of current. Okay, so and whenever we change the direction of current and whenever we change the direction of field produced by that current, we don't want a lot of heat to get released. So we will ensure that the material's VH graph is very, very thin. Okay, something like this. Not able to draw. Yes, something like this. Okay, the VH graph is very, very thin, which means the heat loss per unit volume is very less. So this is called the material that we generally use is soft iron. Okay, it's kind of iron where there are no impurities. Okay, so if you do that, it's you can see that the energy released or heat released is very, very less. So obviously from the graph you can say that the retentivity and coercivity values are also very, very less. So it kind of gives you a very high control over the magnetic field inside the material because there is very, very less retentivity. Now on the other hand, if you want to make permanent magnets, you want how do we make permanent magnet? We'll just go and place a ferromagnetic material inside a magnetic field, and because of that the magnetic field is produced inside the material, and even if you switch off the external magnetic field that material will still retain some magnetic field. Okay, that is basically your permanent magnet. So if you want a good permanent magnet, obviously you want the material to retain large amount of magnetic field even after removing it from the external magnetic field, which means you have to choose a material which has very, very high retentivity. So something like that. Yeah. So this material has very high retentivity. So even after you remove H and make H 0, you still have a very large value of magnetic field inside. Okay. So very high retentivity. So what is an example, guys? You guys remember any example? What is that? I forgot the name. It's an NCRT. Yes, remember that. What is the name of that material, guys? Which we use? What is that? Hmm. Neodymium. Yes, yeah, neodymium magnets. Not sure about the spelling neodymium. Just look up NCRT ones.
Neodymium.
So DY, yeah. Okay, whatever, guys. Just look at the spelling. Look at it in NCRT. So this material has very high retentivity. So that's why we use it for permanent magnets. That's all, guys. That is what you need to know about hysteresis. So any questions before I move on to EMI? Okay. Next, let's start EMI. So we use magnetic flux heavily in this chapter. So we need to know exactly what's magnetic flux. Magnetic flux is integral B dot dA. Okay, its representation is phi B. B for magnetic. Okay. Now, if area is constant, sorry, if B is constant, okay, for uniform B bar, okay, if magnetic field is constant, you can take it out of the integral and then you can just write B bar dot integral dA bar is nothing but A bar. Okay, so in a lot of cases, you will be given magnetic field which is uniform. Okay, very, only occasionally you will get cases where magnetic field is not uniform. In that case, you'll have to do integration. But otherwise, it's just this B bar dot A bar. So what we're going to do is we're going to find out magnetic flux through an imaginary loop. Okay, so I have an imaginary loop, which means it doesn't really exist. It only exists in our mind. Okay, so I would like to find out the magnetic flux. Now, in the formula for magnetic flux, you have B bar dot A bar, and that dA bar or A bar over here, it's the area vector. Okay, now when you take this loop, I can say that this is the area enclosed by the loop. Now, what is the direction of the area? Okay, so area enclosed by the loop can be assigned two different directions. We can say its direction is inwards or its direction is outwards. Okay, so based on that, we define a flux inwards. Okay, magnetic flux inwards or into the loop. Okay, inwards or into the loop is given by B bar dot A in. Okay, so if you are finding magnetic flux into the loop, then the area vector must be going into the plane of the screen. Okay, similarly, if you're finding flux outwards, okay, or flux out of the loop, again, you'll do the same thing, B bar dot. In this case, you will take the direction of area vector to be out of the screen. Okay, so a very simple example can be like this. You have a circular loop, imaginary loop again, of let's say 1 meter, and there is a magnetic field in the region enclosed by the loop. Okay, something like this. Uniform magnetic field is there, and that is equal to, let's say, 2 Tesla. Now, I'd like to question is this: find the flux into the loop. Find the flux into the loop. So I'll do that. B bar dot A into the loop, right? So A in. So magnetic field is 2 Tesla, and the direction is inwards. How do I know the magnetic field is inwards? Because there is a cross sign here. Cross means inwards, right? Cross means into the plane. And the direction of area vector is also into the plane, right? So B bar and A in, they're in the same direction. They're both into the screen. So the dot product will be simply that. Okay, plus B into A in. So that is 2 into pi into 1 square. That's basically 2 pi. Okay, so we can say Tesla meter square, or we can also say Weber. Okay, Weber means that is the spelling. Okay, so that's it, guys. That's how you find out flux. And if in the question they're saying flux out of the loop, again you do B bar dot. This time you do A out. Okay, so B, the magnetic field vector B is into the plane. Area vector now is out of the plane. So the dot product will be minus B into A out. So that is minus 2 into pi into 1 square. Okay, that's basically minus 2 pi Tesla meter square or Weber. So that is about flux, guys. Okay, so flux through a loop. is what we are finding. And they can ask you two kind of questions: flux into the loop or flux out of the loop. If you're asked to find flux into the loop, you take area vector inwards. If you're asked to find out flux out of the loop, you take the area vector outwards. That's it. So that is about flux. Any questions, guys? Any questions before I move on to Faraday's law? Okay, right. So let us, yes, Faraday's law. So according to Faraday's law, the induced EMF, which is also given by integral E bar dot dl bar, is nothing but minus d by dt of the flux. Okay, so what does this mean? If you have an imaginary loop, again, imaginary doesn't really exist. So let's say there is a magnetic field, okay? And so if you find out integral E bar dot dl bar for this loop, what is the meaning of finding integral E bar dot dl bar? You go around the loop, okay? And then find out E bar dot dl. Okay, so let's say at that point electric field is like this. Okay, so from here to here, find out E bar dot dl bar. Okay, once you do that, go jump forward again for that dl bar. Again, find out E bar dot dl bar. Jump forward again, find out E bar dot dl bar. Jump forward again, find out E bar dot dl bar. Then just add all of them. Okay, so that's what integral E bar dot dl bar means. So that is equal to minus d by dt of flux. So now direction is very important here. What does that mean? So in this case, in the diagram, I'm traveling in the anti-clockwise direction around the loop. You can see the direction of arrows, right? They're going in the anti-clockwise direction. So integral b bar dot dl bar found in the anti-clockwise direction is equal to minus d by dt of flux that is coming out of the screen. Okay, similarly, if you're finding integral E bar dot dl bar in the clockwise direction, that will be equal to minus d by dt of phi into the loop. Okay, so that's one thing that you need to be careful. The sign can be sometimes, it can create mistakes. So this integral E bar dot dl bar is also called EMF. By definition, EMF is the work done per unit positive charge as the charge moves from one place to another place. So by that definition, this is simply EMF. Okay. So since we are finding integral E bar dot dl bar in the anti-clockwise direction, we call this as anti-clockwise EMF. Anti-clockwise EMF is nothing but minus d by dt of flux outwards. Similarly, clockwise EMF is nothing but minus d by dt of flux inwards. And that's it, guys. That is Faraday's law. So let us look at a simple example and see how it works. So we have a region where magnetic field is inwards like this. And there is an imaginary loop like this, okay, whose area is, let's say, 3 meters square. So in that loop, the question is, find anti-clockwise EMF induced in the loop. Okay, what do? Well, you don't have to do anything. Faraday has done it for you. So according to Faraday, anti-clockwise EMF is equal to minus d by dt of phi b out. So phi b out, right? Flux that is going outwards is nothing but so you can see here b bar dot a out. Okay, so that is minus d by dt of, so b vector is inwards, right? And area vector is outwards. So the dot product will be negative. B is 2t and area is 3. Okay, so if you differentiate that, you'll end up getting 6. So anti-clockwise EMF is nothing but 6. The unit is volt, 6 volt. Okay, that's all, guys. If you're trying to find out clockwise EMF, so clockwise EMF, that will be minus d by dt of phi b inwards. And if you do that, you're going to get minus 6 volt. Okay, so simple. Any questions in Faraday's law and its application? Please let me know.
No, sir.
Okay, next. Once we know what is Faraday's law, next thing is we can actually solve some questions now. Induced current. Earlier, we have taken an imaginary loop. The previous question, we had an imaginary loop. Now, let's take a loop which is actually made of some conducting material. Okay, conducting material. What happens now? So, we have earlier found out that there is an EMF in this loop. Now, if you replace that loop with a conducting wire, okay, conducting loop of wire, that EMF which is actually induced here is going to drive some current through the loop. Okay, so already we found out the clockwise EMF. Okay, clockwise EMF is equal to, in the previous question, we found out that it is minus 6 volt. Okay, or anti-clockwise EMF is 6 volt. Okay, this is what we found in the previous question. Now, if you replace this loop with a conducting, actual conducting wire, this induced EMF is gonna induce some current called induced current. Okay, and how do I find out that current? Very, very simple. So you take that loop, okay, and in this loop there is an induced EMF. Okay, how much is that? There is a anti-clockwise EMF of 6 volt. Okay, so I'm gonna place a battery, a 6 volt battery, which is gonna drive current in this loop in the anti-clockwise sense. I could have also done it like this. I could have taken this loop, and then clockwise EMF is minus 6 volt. So I'll put a battery of EMF minus 6 volt, which will run a current in the clockwise direction. Now, if you see both these circuits, both are actually same, right? So a 6 volt battery driving current in the anti-clockwise direction is same as a minus 6 volt battery running current in the clockwise direction. Both are exactly same. Anyway, so what all you have to do to find out induced current is replace that induced EMF with a battery. Okay, and this is a simple current electricity question. Now, if you know the resistance of the wire, all you have to do is I is equal to 6 by R. Okay, for example, resistance is given as 10 ohm, let's say. So it's just 6 by 10, that is 0.6 ampere anti-clockwise. Okay, here if you want to do it, again, we'll say I is equal to minus 6 by R. So that is minus 0.6 ampere clockwise. Okay, so we can say 0.6 ampere clockwise, sorry, 0.6 ampere anti-clockwise, or we can also say minus 0.6 ampere clockwise. Both are same. Okay, so that's it, guys. The way we find out induced current is you replace the EMF produced by time varying flux with a simple battery. Okay, and that's it. So any questions here? Any questions in finding induced current? Please let me know. Okay, Then do it here itself. So a very common question is this. You have a conducting rail. Let's say it has some resistance here, some 2 ohm resistance. And then we have a movable rod which is running along the rails with let's say velocity of v, okay, and the length of the rod is L. So the question will be like this: find the induced current. Okay, so same thing. I'll find the induced current by replacing the EMF with the battery. So for that, first of all, I'll have to find out EMF. Okay, to find out EMF, what I'll do is I'll take this area. Okay, let's say this length is X. So I'll find out flux. Okay, so I'll find out flux out of the loop. That will be B bar dot A out. B is, let's say, some 2 Tesla. Okay, so B is inwards, area is outwards. So this dot product will be minus 2 Tesla into the area. Well, you can see area of that shaded region is a rectangle, so it's just length into breadth, right? So L into X. That's all. So now I'll use Faraday's law. According to Faraday's law, anti-clockwise EMF is minus d by dt of phi out. Okay, so that's it. Minus d by dt of minus 2 Lx. So that is 2 into L into dx by dt. Okay, so dx by dt, you can see from the diagram, it's just equal to velocity. Okay, the rate at which x changes is nothing but v. Okay, you can think of this point. Let's say this is your origin. So that point's position is basically x comma 0. And if you differentiate that, if you differentiate the position x, you will end up getting velocity v. So dx by dt is nothing but velocity v. So you get 2lv. Okay, if you remember, you can also do this from motional EMF. We have a formula BLV, right? So it's exactly the same, in fact. Okay, you can find out that motional EMF BLV, or you can also find that EMF using Faraday's law. That's it. So once we find out EMF, what do? We replace the EMF with a battery. So we're gonna do that. Anti-clockwise EMF is 2lv, it seems. So I'm gonna put a battery which will drive current in the anti-clockwise direction. Its EMF is that. So resistance is 2 ohm. That's it, guys. So the current I in this is by Ohm's law, 2lv by 2, that is L into V. Okay, in the anti-clockwise sense. So that's how we find out induced current. We first find out induced EMF using Faraday's law. And once we find out induced EMF, we just have to replace replace that EMF with a battery, right? And once we replace everything with a battery, it's just a current electricity equation, and we can solve the circuit and find the currents. So that's an example. So tell me, guys, if you have any doubts, please let me know. I'll explain it again. Any questions?
So can you explain the question again? Like the
Yeah, you understood how I calculated flux, outward
yeah,
flux? Okay, that turned out to be minus 2 into L into X. So that is clear, is it?
yeah,
So apply Faraday's law. According to Faraday, anti-clockwise EMF is minus d by dt of phi out.
okay,
So yeah, you just differentiate minus to Lx, and eventually you'll get 2 into L into dx by dt. And dx by dt, rate of change of position, is nothing but velocity v.
yeah,
Okay.
yeah. Thank you.
All right. Any other questions, guys? Okay. Then let's look at another question. So in this particular question, the loop is fixed, it's not moving, okay? But then we're going to produce induced EMF by varying the magnetic field, okay? So there is a loop, current, conducting loop, whose resistance is, let's say, 10 ohm, and the side of the loop is 2 meter. It's a square loop. Question is, find the induced uh, current at t is equals to 5 seconds. Okay, same thing as they're asking us to find induced current. What do we do? First, we find out EMF, and then from that, we'll find out current. Let me find out EMF first. So, how do I find out? Well, according to Faraday's law, let's say clockwise EMF is equal to minus d by dt of phi inverse. I'm going to apply that. So, minus d by dt, phi in is b bar dot a in, area vector a in, right? So that is it. B bar is 40 square. A in area, magnitude of area is 2 into 2, 4 meter square. Area is direction of area is inwards. Magnetic field is also inwards. So you're going to get plus 40 square into 4. So you minus 16 d by dt of t square to t. That's it. That is the EMF. Okay. So we can replace this with a simple battery now, okay, which pumps current in the clockwise direction, and it has a EMF of minus 32t. So let me do that then. This is the loop, and this is the clockwise EMF, and its voltage or its EMF is minus 32t. The t is the time, okay? Simply means that EMF varies with time. It's not constant, unlike in the previous question. So this current I is equal to V by R, right? So minus 32t by R. R is given as 10, so minus 3.2 into t. Now they're asking us to find the induced current at t is equals to 5 seconds. Then I is equal to minus 16. Okay. So at t is equals to 5 seconds, there is a current in the clockwise direction, and that current is actually equal to minus 16, it seems. Well, minus 16 ampere clockwise is basically 16 ampere anti-clockwise. Okay, so the current is actually anti-clockwise is equal to 16 ampere. So that's it, guys. Very simple, you know. Yeah. Any questions now? Any questions in this? Uh, any doubts in this question? Hmm? Okay. All right then. Next, let's look at Lenz's law. So Lenz's law talks about the direction of induced current in a loop. So before that, we have to recollect some things. If you have a loop and there is a current I in the loop like this. Now, if you look at the field produced by this current, okay, field produced by this current carrying loop, by using right hand thumb rule, we can say that current will, magnetic field will be developed upwards inside the loop. Similarly, if you have, let's say, a loop like this and current is clockwise, again, by using right hand rule, I can say that the magnetic field is inwards. Okay, so this much we need to know. Okay, if you given the direction of current in the loop, we should be able to find out how the magnetic field is at the inside the loop. Okay. So now let's apply Lenz's law. Let's see what is Lenz's law. So there is a magnetic field outside which is increasing. Okay, so the flux through the loop, the flux into the loop is increasing. Okay, flux that is going into the loop is increasing. So according to Lenz's law, induced current in this loop will be induced, right, in such a way that it opposes the change in flux. Okay, induced current should oppose the change in flux. So what is change in flux? Let's see how flux is changing. It is increasing into the loop. Okay, flux is increasing into the loop. To oppose that, we have to make sure that the induced current produces a magnetic field outwards. Okay, inward flux is increasing. So how do you oppose that? Create an outward magnetic field. Okay, flux is increasing inwards. Oppose that by creating a field outwards. So if you want to create an outward magnetic field, you have to make sure that the induced current is running anti-clockwise. So this anti-clockwise running current will produce a magnetic field outwards, which will counter, which will oppose the flux that is increasing inwards. Okay, that's it. So let me show you some examples. Let's say this is magnetic field. So now let's say this magnetic field is going down. What this means is flux that is going in is going down. So flux inwards is going down. How do you oppose that? By creating a magnetic field inwards. Okay, which means current must be clockwise. If you create a clockwise current, then the field produced by that clockwise current will be inwards. Okay, so next example, let's take a magnetic field that is out of the plane like this. Okay, let me just draw it here. So that's the magnetic field. It's going outwards, and its value is increasing, let's say. And then in between, we have a loop like this. So now the magnetic field out of the plane is increasing, which means the magnetic flux out of the plane is increasing, right? Magnetic flux out of the loop is increasing. To oppose that, magnetic flux outwards is increasing, right? So flux outwards is increasing. How do you oppose that? Create a field inwards. Clockwise. Yeah, very good. Okay. That's it, guys. So that is Lenz's law. Okay. So is that clear, or any you need more explanation? Please let me know. Any questions there?
So how is this related to conservation of energy?
You can link it to conservation of energy, uh, but this is not the right time to discuss about that. Okay, we'll keep it basic here. Okay.
Okay.
Yeah,
But is it like in the syllabus?
it's not. No, they won't ask you things like how is it related to conservation of energy. At the end of the day, conservation of energy is always there. It is always running in the background. Okay,
Right. Like I understood how to solve these questions, but I
hmm.
don't understand how it's related to conservation of energy.
Why are you thinking in that lines actually, or in those lines? Why do you want to see how it is related to conservation of energy?
And like if I do understand
Ah.
why how it's related to conservation of energy, so it'll be more satisfying solving those questions.
Okay, satisfaction is it? Uh, I can give you an example where that happens, so maybe that can satisfy you. So in Lenz's law, you'll get questions like these where you have a loop like this, and there is a magnet going down. So I'm explaining this question because it's part of what I was trying to discuss. So in this only, I'll explain the conservation of energy. So you'll get questions like, what is the direction of induced current in this loop. Okay, so what is the direction of induced current in this loop? Magnetic field is inwards, right? It's going like this because of the magnet, and that magnetic field is also increasing because of the magnet is coming closer. Okay, so the magnetic field into the loop over here is increasing. To oppose that, current will be in this direction. Okay, and so the magnetic field produced by this induced current will be upwards like this. Okay, so induced current is this way, and the magnetic field created by that induced current is upwards. Now, so that is Lenz's law. Okay, now here tell me, how is the force acting on the magnet? Is this induced current applying any force on the magnet? Tell me. Conservation of energy guy, tell me. Is this going to apply any force on the magnet? What do you think? For conservation of energy to be valid, how should the force be acting on the magnet? You tell me that.
So it will slow down the magnet, right?
It has to slow down. Why?
Because the field is against the magnet.
Yeah, so can you see conservation of energy happening here? Can you see? So there is current in the wire, right? So there will be a continuous heat produced in the wire, isn't it?
Yeah.
So where is that energy coming from?
Is that the potential energy of the magnet changing? I don't understand.
Yeah, the mechanical energy of the magnet basically is going down. Okay,
Okay.
so that mechanical energy is getting converted into heat energy, right?
So basically, the magnet will first of all fall slower,
Mm-hmm.
and then heat is also generated in the wire.
Yes.
Okay.
Okay.
Okay, fine.
All right then. So let us move on. Let me just see how many students are remaining. It's me versus Rohit Sharma right now. How many students can I attract? Not many. Rohit Sharma is winning. Okay, fine. All right. So that's Lens law, guys. Next, yeah. By the way, how is this repelling the magnet? Why am I saying that? This is slowing down the magnet. Just observe the loop. Okay, that's how the loop is. It's having a current like this. It's creating a magnetic field like this. Okay, which means that the top face of the loop is acting, right? The top face is acting like a north pole, and the bottom face is acting as a south pole. You know, magnetic field lines originate from north pole, so you can see the top face is where the magnetic field lines are originating from. So top face is acting as a north pole, bottom face is acting as a south pole. So when you have a magnet whose north pole is closer to the loop, so these two north poles, which are close to each other, are repelling. Okay, so that's why the magnet sees an upward force. Okay, magnet slows down. So that's what it is. Okay. So any questions on Lenz law further before we move on?
No, sir.
Okay, then let us look at next thing, that is motional EMF.
So basically, if you like put a pass a magnet, like throw.
Wait, listen. Okay,
Yeah.
after 9 o'clock, I'll still be here. You can ask. Okay.
Okay. Okay.
So motional EMF, in this case, we have a magnetic field. Now, what we are doing is we have a wire like this, okay, and it is having a length L and a velocity V. So the question will be like this: what is the EMF induced across the rod? Okay, so EMF across the rod. Right. So what we do is to find out this, well, we take a small positive charge that is inside the rod. Okay. And since the rod is moving at velocity v bar, the positive charge is also moving at velocity v bar. Okay. So then I'll find out the force acting on that positive charge. And I know this formula. And I'm taking a 1 coulomb charge. So Q is 1. So it is simply that. Now, if you look at the work done by that force, okay, work done by that force as this positive charge moves like this. Okay, as the positive charge goes from one end of the rod to the other end of the rod, the work done by this force is nothing but this F bar dot displacement L bar. Okay, that will be V bar cross V bar dot L bar. That's it. So that is the work done. And if you remember the definition of EMF is nothing but work done per unit positive charge as it goes from one point to another point. So that's what we found out, right? We found out the work done per unit positive charge as it goes from one point to another point. Therefore, that's what our EMF is. That's it. Okay, so that's the formula you need to remember. I hope everybody knows how to do cross product and dot product. So let's use that and look at a few examples. So magnetic field of 4 Tesla is there, and there is a rod. I'm going to place the rod like this, okay, which is making an angle of 30 degree, let's say like this, or let's say 60 degree. Yeah, so now this rod is moving with the velocity, which is 2 meter per second, and the length of the rod is 3 meter. Okay, so the question is from A to B, what is the EMF? All I have to do is apply the formula V bar cross V bar dot L bar.
Sir, I can't
Yeah.
see your screen anymore.
Oh, is it? Is it the same for others also?
No, sir. I can see it.
See, right? Just reload and see whether it works or not. Okay, so this particular question can be done in different ways. I'll just show you one way, then we'll also see another easier method. So V bar cross V bar dot L bar, right? We have the vectors ready with us, okay? And first thing is we can find out V bar cross V bar. And V bar is horizontal, V is into the plane. So the dot product, the cross product is simply B sine 90. That is the magnitude. And if I use right hand rule, the direction of V bar cross V bar turns out to be upwards. Okay, the direction of V bar cross V bar. V bar is this way. V bar is into the plane. So V bar cross V bar turns out to be upwards. Okay, for this you have to use right hand rule and figure out yourselves. Okay, V bar plus V bar's direction is upwards. So I'm gonna draw it like this. Okay, PV sine 90 upwards dot L bar. Sine 90 is anywhere 1, so it is BV in the upward direction. Okay, going up, right? Dot L bar. It's just dot product now. Upward direction, and if you look at the rod, it is like this, an angle 60 degree. So the angle between BV upwards and L bar, you can see from the diagram is 30 degree. Okay, so finally what you get is BV into L into cos 30. Okay, so that's it, guys. 4 into 2 into L is 3 into cos 30 is root 3 by 2. So that is 12 root 3 volt. Okay, so it's just a simple cross product dot product. Okay, if you know how to do that, then you can easily solve this. We can also solve this in a slightly easier method, mathematically easier. So let's just see how that is. Ah, yeah. So in these kind of questions, what you can do is break the rod into two components, horizontal component and vertical component. So this is 3 meter, so 60. So this will be 3 cos 60, which is 3 by 2. This will be 3 sine 60, that is 3 times root 3 by 2. So once you break the rod into two components, you can find the EMF across each of the two components. And if you find out V bar cross V bar dot L horizontal bar, okay, you can figure out that it is going to be 0. Why? Because V bar cross V bar, already we have seen that it is upwards like this. Here, vertically, in the vertical direction. So if you do the dot product with horizontal LH, right, horizontal LH bar, you're going to get a 0. Simple. Okay, so if you look at this vertical component of the rod, for that you're going to get a L vertical. Okay, so that is going to simply give you B into V into the vertical component of L. Okay, just do the dot cross product and the dot product, you'll easily get this. So 4 into B is 2 into LB is 3 root 3 by 2. That will also give you 12 root 3 volt. So in these kind of questions, what you can do is you can break the rod into components. Okay, and find out the EMF due to each of the components and add them. Mostly, the reason why we break that into components is one of the components EMF becomes 0. So in this case, this horizontal component has an EMF that is equal to 0. Okay, so as a point to remember, just remember this. Whenever the rod slices through the field lines or slashes through the field lines, you will have induced EMF. Okay, what does that mean? If I have a rod like this and it is moving along like this, on its way, it's going to slash through these field lines. It's going to cut the field lines, right? So whenever that happens, you will have EMF. And for example, if the rod is moving like this, it is not slashing through, it is not cutting through any field lines, right? It is nicely sneaking in between the field lines without slashing them. So if you find out EMF, it will be equal to 0. Okay, so that's a nice thing to remember actually. Instead of doing cross product dot product, just to see if there is an EMF or not, you just do this. Whenever the rod slashes through the field lines, there will be EMF. Whenever it doesn't slash through the field lines, there won't be any EMF. Okay, so that's it, guys. That is the formula for motional EMF. So we'll continue from here on in the next class. So if you want to ask something, you stay back. Otherwise, you're free to leave. Thank you so much.
Thank you, sir.
Thank you, sir.
Thank you.